Okay, so this lesson is an extension of the previous lesson. So in the previous class, we learned about orbitals, quantum numbers, and electron energy diagrams. So in this one, we're going to learn about electron configuration. So how to use words and symbols to represent electrons in various different atoms. All right, so the first thing we're going to do is just a review of energy diagrams. So just again to remind you that the number that you see, 1, 2, 3, 4, those are the energy levels, so N. The letters that you see, S, P, D, F, those are the types of orbitals, so that's L. And in the diagram, a dash means one orbital. Okay, so if you look at that diagram on the bottom, all of the dashed lines, the orbital in the same energy level, they're perfectly level with each other. They're in the same row, okay? Meaning that they have the same energy. So if you're at energy level 3, the S, P, and D, they're in the same level, same energy. That's not true though. This only works for hydrogen only, okay? Because hydrogen has only one electron. So there is no interference between different electrons. So you can accurately predict the energy of that one electron in hydrogen. Good. Problem is, if you have more than that, all the other atoms have more than one electron, this doesn't work anymore. So that energy level diagram where everything is flat is actually wrong. And more accurate depiction of energy levels is this picture. So on the picture to the right, you can see that they're not exactly perfectly level between the different energy levels. So this is something called electron configuration. Okay, this tells you the location of the number of electrons in an atom. So in the first level, you have 1s. Okay, that's on the bottom, nothing interesting. There's a huge jump to go to 2s, and then a little jump to go to 2p. So 2s and 2p are in the same energy level. The next shell, you have number 3, 3s, 3p, but where is 3d, right? In the third level, there should be sp and d. Well, you can find 3d in the next level. It's beside 4s and 4p. So in fact, 3d has such high energy, it exceeds the energy of 4s. So actually, 4s comes after 3p, and then it's 3D, all right? And then after 3D, you have 4P, and then 5S, and then 4D. So 4D also has high energy. It exceeds 5S, so it rises above. So 5S, and then 4D, and then 5P. And then the next one is the F orbital. Remember, level 4 has SPD and F, so the F orbital is even higher. It's all the way in level 6. So 5p, 4f, and then 6s. Okay, so the order is important. It is confusing if you just look at this diagram, so it's really difficult to remember the order. So there will be an easier way to help you remember the order of the energy levels. Now, to put electrons in here, you have to follow 2 principles. Okay, the first one is the Aufbau principle. That simply says you got to start from the bottom. All right? Start from the lowest energy level, that is 1s. And then after you fill that one, you can move on to the next energy level. All right? So fill 1s, only then can you move on to 2s. And then you got to fill 2s. Only then can you move on to 2p. So that's the Aufbau principle. So the Hund's rule, the next one, that means you can only pair them up if you absolutely have to do it. Okay, if you see space, if you see an empty orbital, you use that one. You don't pair up if you don't have to. Okay, it's like imagine you get on a bus, the bus is completely empty, and there's one person on the bus sitting somewhere. It is really messed up to just go up to that person and sit beside them, all right, because the bus is empty. That person will be like, yo, is this guy trying to murder me or what? So you don't sit beside another passenger unless you absolutely have to, right? That's typical behavior, right? Same thing here. electrons are negative, you don't want to be near another electron. So you would share an orbital only if you have to. So those are the two rules that we need to fill out the energy diagram. So if you look at the aluminum Bohr-Rutherford diagram to the left, we know that Bohr-Rutherford diagrams are wrong. So we're going to fill out this energy level diagram for aluminum. And aluminum, if you count, it has 13 electrons. So where do we put the first one according to the Aufbau principle? It's got to be 1s. Okay, it's like that Drake song. Started from the bottom, now we're here. You start from the bottom. 1s, you get the first electron. And the second one also goes in 1s because you have to fill it up before you can go to the next one. So that's your second electron. The third electron has to now go to 2s, that's the next level. So 2s, and then you have to fill that level before you can proceed to 2p, so you got to fill it. So there's your fourth electron. So starting number 5, you have 2p. Now here is where Hund's rule come in. You can't fill up the first 2p with a second electron. Okay, you have to evenly spread them out. There's an empty 2p right there. Why would you like squeeze with the first electron? That makes no sense. So take the empty orbital, and then yet there's another one, so you take that empty orbital. So now you have 1 electron in each 2p orbitals. That's 3. Now you have to fill out another one because you have to go to 13. You're not at 13 yet. So only then will you pair the electrons. So now it would be the time where you have to do it. So you pair up. The 3 electrons pairs up, so you now fill the p orbitals. We still don't have enough. Right now we've only used 10 electrons. Aluminum has 13, so 3 more. So now you filled out the p, you can move on to the next level, which is 3s. You get 1 and 3s again because you have to fill out 3s. And now you're at 12. 1 more electron. It has to be 3p. So this diagram right here is the electron energy diagram for ground state aluminum. Ground state means no electron is excited. There is no additional energy given to the electrons, so they are in the lowest possible state. Okay, so that's aluminum, 13 electrons. So Aufbau principle, Hund's rule, they always apply. Make sure you know how to do this. Now, it's silly to draw diagrams for every single atom. Okay, there's got to be a better way. You don't want to draw a picture if you can just write. So instead, we have a writing system, notations, to represent orbitals and electron configuration. And there are 2 types of notations. There is the full notation and the core notation. We're going to talk about the full notation first. So the full notation simply means you just write out everything you possibly can. So if you look to the bottom right, you see a 3p5 right there. The 3 refers to N, your energy level. P refers to the type of orbital. In this case, that's the p orbital. The superscript 5, this is not math class. Okay, that is not to the power of 5. That is not an exponent. This means you have 5 electrons in the p subshell. This is pronounced 3p5, not 3p to the power of 5, simply 3p5. Okay, it means 5 electrons in p. It doesn't mean raise p to the power of 5. So you start in the lowest, 1s, and you work your way up. So instead of drawing, you just write this out. So you indicate the number of electrons using a superscript right after the orbital type. So an example for aluminum will be 1s2, 2s2, 2p6, 3s2, and 3p1. Okay, I did it in order from the lowest energy level to the highest one. Okay, does that make sense, guys? The 3p1, well, there's a 1 because there's only 1 electron in the entire 3p subshell. You have to write the 1. It is not redundant in math class. You don't write the exponent if it's 1, but no, here you have to. You got to write all the numbers. Okay, so this is aluminum. If you see that, you just count the number of electrons. You count 13 because you add up all the numbers, you should get 13. That kind of tells you that this has the electron configuration of the aluminum atom. All right, and this is the electron configuration for the first 10 elements. You can see that hydrogen is just 1s1, helium is 1s2. Now, there's a picture that comes with it too. Hydrogen has a little sphere. Okay, that represents the 1s orbital. Helium also has that sphere, as helium also uses the 1s orbital. But that one is a little bit darker. This is just an artistic depiction trying to tell you that, hey, this orbital has 2 electrons instead of 1. That's why it's darker than the hydrogen one. If you go to the next row, lithium, 1s2, 2s1. It has 2 different balls, one embedded within a bigger one. That smaller sphere, that is the 1s orbital. The bigger sphere is the 2s orbital. Beryllium is just 1s2, 2s2. You have 1 additional electron, so the artist depiction makes the 2s orbital a little bit darker, just telling you that, hey, there's another electron here. Boron has p orbitals now, 1s2, 2s2, 2p1. So the p orbitals are dumbbell shaped. You can see that one of them is colored in red, telling you that, hey, there's an electron in here. Carbon has another p, so it's 2p2. And then nitrogen, 2p3. Notice that they all have a different p orbital because they occupy different p orbitals. You only start to double up at oxygen because you have 4 electrons in p. You got to pair up one of them. So one of the lobes is darker. And then you have fluorine, and finally neon. Neon has a full electron configuration. All of its orbitals up to 2p6, they're all full, okay, which makes neon inert. You don't need any more electrons. You better not take my electrons because this is perfect. Everything is filled just right. Okay, so this is the electron configuration for the first 10. Now, obviously, we're not going to just end at neon. You're going to know how to do all of, well, most of these, not all of them. So how do you remember the order? You don't memorize straight up, okay? Unless you're crazy and you want to play life on hard mode, okay, go ahead and memorize it just straight up. But there are tricks. And my favorite one is the periodic table method. If you just check out this periodic table right here, it's color-coded in 4 sections. If you just imagine you move the helium tile you just all the way to the left to put it beside hydrogen. So on the left 2 columns, the alkali and the alkaline earth, plus the hydrogen and helium, those make up the S block, okay? That means elements found in those regions of the periodic table, they end with an S orbital. Okay, the yellow ones on the right, they're the p block, element found in those regions. The electron configuration ends in p's. And then in the middle, the transition metals, you have the d block. And then on the bottom, you have the f blocks, okay, the lanthanides and the actinides. Keep in mind that the lanthanides and the actinides, the green portion of the periodic table, it is situated in between lanthanum and the following element, okay? Once you hit lanthanum, you actually go to the 4F block, you read those elements first, and then you go back into the D block. The reason we don't put it in, because then the periodic table would be too long and it wouldn't fit on a piece of paper nicely, so we take it out to make it more convenient. But you have to know the order in which the atomic numbers go, and the F block follows lanthanide, and then you go to 5D, okay? Now, this is very easy because you all have a periodic table, and you're allowed to use one for the test, so you might as well just take it out and just go across the rows. You can just go, well, 1s goes first, and then you have 2s1, 2s2, and then you have the 2p's all the way to 2p6, and then 3s1, 3s2, and then the 3p's all the way to 3p6, okay? And then you have the 4s1, 4s2, followed by the 3Ds. You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You go all the way to 3D10, and then you have the 4p6. You go 1, 2, 3, 4, 5, 6. Does that make sense? You just keep going. Right? And this actually tells you why the first, well, orbit, if you learn orbits in grade 10, the first orbit has a maximum of 2 electrons. The second orbit has a maximum of 8. Because you only have the 2s and the 2p, they add up to 8 electrons. The third orbit has 8 electrons, not 18, because 3s and 3p add up to 8. Now, what about the other 10 electron? Well, that's in the 3d, and the 3d is not found in this third row because its energy is too high. It's been pushed beyond 4s, so you actually find it in the fourth row. Okay, so that's why the first 3 rows is 2, 8, and 8, and then you stop at calcium because it gets crazy into the transition metal. That's why grade 10 students don't do it. So anyway, let's go to 5s. So you go 5s1, 5s2, and then you will go through the 4ds, so all the way to 4d10, and then 5p6, then you finish at the noble gas, and then you go to 6s, 6s1, 6s2. Now it gets messed up. The f orbitals fit next, okay? You will go through these guys. There are 14 elements here, 4f14, and then you will go through the 5d10, and then you go to 6p6. You have to go in order horizontally, and if you have a periodic table in front of you, this should tell you who comes next. Just follow the horizontal rows, and you know exactly what comes next, okay? If you don't like this for some reason, there's another method on the left side. If you just write out all the orbitals, 1s on the bottom, higher up you have 2s, 2p, and then 3s, 3p, 3d, and then all the 4s, all the 5s, all the 6s, all the 7s aligned together, okay? And then you start drawing diagonal arrows from bottom right to top left. And if you just draw those arrows, the order in which it pierces the orbitals is the order that they appear. So the first one will be 1s, and then the next one is 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. You get the idea. If you want, you can do that. This also tells you the order of the orbitals. But I don't like that one. That's just personal preference. I like the periodic table way more than that. Well, because it's available, I don't have to draw that out. So you do you, okay? Like whatever floats your boat, figure out the order. You have to know the order. I won't give you the order, so I expect you to actually know it. So let's actually apply this. Okay, so let's do the electron configuration for the element francium. And francium, where would you find francium on the periodic table? So you whip it out, you take a look, and then you quickly realize that francium is on the bottom left corner. All right. Francium is in the 7s block. So if you look at the diagram below, francium is bottom left. So how would you write the electron configuration for francium? I'm going to give you some time to do this. I'll give you a minute. Write out the full electron configuration. I know it's going to be long. I chose francium because I actually want you to go through with all of these just to practice the different orders and the numbers. All right, so 1 minute and I'll take this up. All right, so I'm going to show you the electron configuration of francium. You simply start at 1s, you just go through the list, and until you end up at 7s1, you're finished, okay? So 1s2, because there's 2 electrons in s, 2s2, and then the next one will be 2p6. Notice that you need 6 electrons to fill up p, so that's why you got a 6. 3s2, that will be the next row. 3p6, again, 6 electrons to fill up 6, that's the next block. And then you move to the next period again, 4s2, but then you have to go to the D block now, 3d10, there are 10 transition metals across, okay? So, well, it's not an accident there's 10 transition metals across because there are 10 electrons in the D block. And then you have 6 elements that comes after, so that is 4p6, and then to the next row, 5s2, same story, 4d10, and then 5p6. So the next row starts with 6s, But remember, what comes after 6s? Well, the F block. You have to insert that into the periodic table. So that would be 4F14. There are 14 elements in the actinides and the lanthanides. Again, not an accident, because there are 14 electrons in the F block. So really credit to Mendeleev for coming up with this brilliant idea for periodic table. It is so convenient. It has a lot of explanatory power. Patterns are everywhere. So after 4F, you have 5D, and there's 10 of those. So 5D10, 6P6, and then finally you arrive at 7S1, because francium is an alkali metal. It is at our first column, so it's S1. So this is francium. All right, I know what you're thinking. You got to be kidding me. I don't want to write this. If this is on the test, then well, that test is going to be long. So there must be a shorter way, and you're right. There is a shorter way. Nobody likes to write this, okay? Like, I never will write this out. I will always take the shortcut. So what is that shortcut? The core configuration. All right, so the idea is this. The valence electrons are the ones that we care about. The inner electrons, they do nothing, okay? They just sit there. They don't ever participate in any chemical reactions whatsoever. So why do we bother writing them out, right? So why do we just, abbreviate that somehow? And you can choose the previous noble gas on the periodic table. So let's say you have bromine, and you can see bromine on the periodic table right there. If you manage to find the noble gas that comes before bromine, and that would be argon, if you just point the arrow backwards until you get a noble gas, the one above argon. Okay, if you can write that, if you can just abbreviate the configuration for argon and then write out what comes after that, it is much faster. Okay, make sure you don't look at krypton, the one after bromine. You have to go back to the previous noble gas. Just because you're sitting right next to a noble gas doesn't mean you can use that one. And also, if you are already looking at a noble gas, you can't just simply use itself. You still have to apply this rule. Find the noble gas that comes before that one, so the guy on top of you, and use that noble gas as the abbreviation, and you have to write what comes after all of those things in the electron configuration. Right, so let me show you this example with francium. So here's francium, the full notation. That's ridiculous. Okay, that's a waste of ink and of time. So let's abbreviate that. The noble gas that comes before francium, the closest one is radon, right there on the periodic table in 6p. All right. So everything I highlighted in blue, that is the electron configuration for radon. You don't have to write that out. All you have to do is write square brackets radon. That's it. That represents all of that nonsense. And followed by 7s1. Okay. Isn't this much easier? You don't have to write out 20 different letters, just the noble gas that comes before and whatever electrons that come after. So this is the core notation. You have to know how to write both because you're learning this for the first time, but realistically, nobody writes the full notation, okay? If I have to write something, I always go for the core. Unless the tests specifically say write the full, you can write the core because it's simply faster. All right, so let's practice. I'll give you 2 minutes for this. 3 electron configurations. I'll try to write the full and the core for practice, and I'll take this up very shortly. All right, so for magnesium, you would have this. Okay, 1s2, 2s2, 2p6, 3s2. That one is quite simple. The closest noble gas to magnesium that comes before is neon. So you can just omit all the way up to 2p6 because that's included in neon. And then what comes after is just 3s2. Okay. Bromine, we had already seen the example. Bromine, if you write it out in full, It goes from at 1s2 all the way to 2p5. Again, don't forget the 3D. Some people will tend to forget that. The noble gas that comes before bromine is argon, so you can omit all the way up to 3p6, that's argon. And then what comes next is 4s2, 3d10, and 4p5. So that is shorter than the full notation. Okay, xenon, people might have an issue with because xenon is already a noble gas. So you are just tempted to write square brackets Xe and be done with it. Don't do that, okay? You can't be that lazy. The full notation for xenon, just from 1s2 all the way to 5p6. Don't forget the 3D and the 4Ds. But the core notation, though, you have to use the noble gas that comes before, which is krypton. And you have to write out everything that comes after that. Okay, you can't be lazy and just write the xenon. That's not how it works. Okay, does that make sense? So compare your answers to these. Make sure you got it. If you didn't get it, find out where you made the mistake and don't make these mistakes on the test.
Wait, so on the test, would you ever ask us to write the full electron configuration?
Yes.
Oh, okay.
I know, like it's gonna suck, but I'll try not to make it long. You're learning now. That's why I'll make you write out all that stuff, just so you get the practice. But on the test, for the sake of your hand and my eyes, I'm not gonna make it that long.
Okay.
If anything, I'll just make you write the core if it's a long one.
Why for bromine did we use argon and not
bromine?
Like selenium, the one before?
Selenium? Oh, yeah. Literally the one before? You have to use a noble gas, right? Because noble gas are considered to have a full valence, a full electron configuration. So those electrons will never ever be touched. They won't do anything. So you can just put them in a square bracket and never worry about them again. The electrons that come after, they might be part of a chemical reaction. So it is helpful for you to write them out. So you can't literally pick selenium, the one before bromine, and just write 4p1. That's not how it works. It has to be a noble gas because they're inert. Those electrons become useless. You see what I mean?
Okay. Yeah.
All right, that's a good question. Nobody ever asked that question before. All right, so that was the normal ones, okay? But there are many exceptions to the rule. And we're only going to learn one kind of exception. All right, this is the exception that we're going to learn. If you have a fully filled or half-filled D subshell, okay, that means you have a D5 and a D10. Okay, D5 means you filled it halfway. D10, you completely filled the D shell. This is actually very stable. This is more stable than D4 and D9. So you prefer the D5 over D4 and the D10 over D9. You prefer so much that you will cheat and you will steal an electron from the s orbital and give it to the D so that the D will complete a set. You see how this works in the picture? You have an S2 and a D4. That's not good. That's not stable. So you rip an electron from the S, you give it to the D. Now it becomes stable. Same thing for F. A fully filled or a half-filled F subshell is actually very stable. F7 and F14 are good. F6, F13, not stable, bad. If you see F6 and F13, what you do is you rip an electron from the S orbital, you give it to the F so that the F will complete its set. All right, so you do this, you don't do this because you want to make it look good. It's because it's more stable that way. Okay, you require less energy to keep it like that than to keep it in the original state. So nature always finds the lowest energy and then it does whatever that is. So make sure that when you write electron configurations, take note, if you ever write a D4 or a D9, you should feel uncomfortable, all right? Like the sight of D4 and D9 should make you sick. Change it to D5 and D10.
I have a question.
Mm-hmm.
For the, like, when we steal, like, the electrons from S,
Yeah.
Which one do we take it from? Like, do we take it from the before one? Like the...
Yeah, okay, good question. You take it from the S that comes before, like immediately before. Don't go reach all the way back to 1S. You take the S that is the largest N.
Okay.
I'll show you another picture on the next slide, and this will be more clear. There was another question.
Yeah, if you have like D1 or D6, does it matter?
If you had a D1 or D6, no, that does not matter. Okay, only D4s and D9s. Now, realistically, I wouldn't worry about the Fs at all, because I will never give you a question where the element is found in the F block. Okay? The reason for that is there are many more exceptions in addition to this rule. And those exceptions, I never seem to have found a pattern with them. So you basically just have to know them. You have to use empirical data to figure out what the electron configuration is, and there's no good way to just remember them. So that's why it's not in the course. I don't expect you to know them. I didn't memorize them myself because it's crazy. But if you just Google some weird electron configuration, just pick your favorite element like americium, Google that one, and check out the electron configuration. You're going to see that, wait, that's not the rule that we learned, because there are many other exceptions. They break the rule, so we don't actually consider them. So on your test, I will only give you the ones that follow the rule or have an exception like this one. Okay, this is the only exception you got to know. So that means you don't have to worry about F, because there are too many weird exceptions in the F block. But D block, that's fair game. The D block actually has very few weird exceptions, and I'll just avoid those. So let's look at chromium and copper, the two classic ones. Chromium, if you just write it out normally, you would have argon with 4s2 3d4. Okay, the sight of a 3d4 should really hurt your eyes. That should sound like fingernails on a chalkboard. You want to fix that. All right, so instead you take the electron from the 4s2, so you make it 4s1, you give it to the 3d, now it becomes 3d5. So that's the actual correct answer. If you give me the 4s2 3d4, you get no marks for that question. Right, and for copper, it's normally it's supposed to be 4s2 3d9, but again, you can't have a d9 because that is less stable than a d10. So in fact, you have to promote an electron from the 4s into the 3d, so you have 4s1 3d10. All right, and this applies not just for chromium and copper. You apply to every single element down those columns. Okay, they all have the same pattern. You never ever have a D4. You never ever have a D9. Is that clear? Now, granted, this rule is not difficult to understand. And I'm pretty sure that everyone will know what this rule is and know what to do. It's just that on the test, a lot of students will probably lose marks because you didn't notice. Right? You failed to notice that this is an exception. I'm going to straight up tell you right now. On the test, there will be exceptions. I guarantee that at least one question will have an exception like this. So if you go through all the electron configuration question and you didn't do a single exception, you know you're going to lose mark. Go back and check which one did you miss. Normally, students lost mark not because they didn't know how to do it. It's because they just didn't see it. Okay, so make sure you go back and double check. Now, again, other exceptions exist. We only care about this one. All right, if you see another weird exception, don't worry about it. And to make you see this even better, if you just look at the electron configuration for the fourth row, especially in the D block, you have 3D1, D2, D3, all the way to D10. With chromium, that says 3D4, copper, 3D9. You can't have that. You must have a 4S1, 3D5, 4S1, 3D10 instead of D4s and D9s. Now, why? How is this possible? If you look at the energy diagram, you notice that 3D and 4S, they're actually very similar in energy. All right, 3D is a little bit higher than 4S, but that difference is quite small. So it doesn't take a lot of energy to extract an electron from the 4S to give it to the 3D. In fact, you have a net loss of energy that way. So you want to have the lowest energy. So if you do that, you actually have lower energy. So what actually happens is those two subshells actually become level. One electron will be taken from the 4S and it will be given to the 3D. The spin will change. Okay, it was a down spin, but now it will change into an up spin. Does that make sense? You always have an up spin if you're alone. You only put a down spin when you have to pair it. Same thing for the next one. If you have 4s2 3d9, those shells, the 4s to the 3d, they will become level, and you take an electron from the 4s, you give it to the 3d. Now this time you don't change the spin because you need a down spin. Okay, so now you replace them back into your periodic table. You should have instead 3d5 and 3d10. I think I hammered that home. Okay, you all got this, right? The only issue is don't forget to do this on the test. Okay, the concept is not difficult, but that can be hard to see. All right, so let's move on to ions. We need to learn how to do electron configuration for ions. There are two types of ions. You have negative ions and positive ions. Now for negative ions, it is very simple. Okay, negative ions mean you gained extra electrons. So if you just gain extra electrons, all you have to do is just continue to add electrons normally following the Aufbau principle and Hund's rule. So what I mean by that is if you look at example 1, chlorine with the 1 minus, so the chloride ion, the normal configuration for chlorine is just neon 3s2, 3p5. Okay, you're missing an electron. The whole point of making negative ions is that you complete your octet. You get enough electrons so that you have a full orbital in the p orbital. So chlorine only needs 1 electron to make chloride. So you add 1. Where would you add that electron? Well, obviously you add it to the 3p, right? The one missing the electron. So that is your last additional electron. So what would the configuration be? Well, it's simply 3s2, 3p6. You just add 1 to the p and that's it. Very simple. If you look at sulfur, same thing. The sulfide ion needs 2 electrons. Okay, sulfur needs 2 to complete its octet. So you need to add 1 there, and you need to add another 1 over there. So total of 2. Now, what would the configuration be? Oh, look, it's 3s2, 3p6. Exactly the same as chloride. Heck, it's exactly the same as argon, the noble gas. Okay, the whole point of being ions is to look like a noble gas. Does that make sense? That means if I just give you the configuration and ask you, okay, what is this? That's a terrible question because it can be many things. It could be argon, it could be chloride, it could be sulfide, heck, it could be phosphide, P3 minus. They all look the same in terms of electron configuration. So there's no way to distinguish between them. So I won't ask you questions like that. Instead, I'll just make you write the configuration given the ion already. Okay, so do we have any questions regarding negative ions? You just continue to add. No? All right, good. The hard one is the positive ions because you have to then remove electrons. So the question becomes, which one do I take? And in what order do I take those electrons? So that becomes difficult. So there are more rules you have to remember. So here are the rules. If you must take some electrons, you have to take the electrons from the largest n first. Okay, if you have a 5, let's say a 5s and a 4d, obviously you take from the 5s because 5 is bigger. See how this works? Now, what if it's tied? Okay, you have a tie. You both have a 5, let's say. So what's the tiebreaker? If you have a tie, then you remove electrons in this order. P before S, before D, before F. Realistically, you don't need the last two. Just remember P before S. I've never seen a question where you needed to use the latter part of that rule. So if you have a tie, the tiebreaker is you take it from the P first, and then you take it from the S. Okay, you gotta know the order here. So example 1, sodium plus. Sodium loses 1 electron to become the sodium ion. It only has 1 valence electron to lose, so it's a no-brainer. You lose that one, okay? So it becomes just bracket neon. That's it. That looks ridiculous, but no, this is the sodium ion. iron 3 plus, okay, if you check out iron 3 plus, which ones would you take? Because you got to get rid of 3 electrons. 4s versus 3d. Well, you got to take it from the 4s because you have to take from the largest n. 4 is bigger than 3. You get rid of those 2 first, and then you have to take away 1 more electron you take from the 3d. So you have, in the end, 3d5. You see how this works, guys? Number 3. Okay, that one is the hardest one. Tin 3 plus. So first of all, let me just say that tin 3 plus does not exist. I made that up. I made that up because I wanted you to show me which electrons you would take first. This does not exist in nature. That is highly unstable. So you have to take away 3 electrons from tin. You have 5s2, 4d10, 5p2. Okay, that is the normal electron configuration for tin. To take away 3 electrons, now you have a choice. You follow the rule, largest n first. Okay, 5s and 5p, they're both 5s. So p before s, that's the tiebreaker. So you got to take from the 5p first. And then after that, you take from the 5s. So you end up with 5s1, 4d10. Right, does that make sense, folks? Again, I reiterate, this does not exist. But if it were to exist, that would be the electron configuration. So do we have any questions?
Neon.
We don't? We good?
Sorry, for the first one,
The first one. What about the first one?
we just leave it like neon.
Yeah, you just leave it like neon. Nothing else. That's it.
Okay.
Okay, so before we move on, I just want to briefly mention something very interesting here. You may have had the question in grade 10 when you had to learn about multivalent metals. You know how iron, it can make 3 plus or 2 plus? Well, why? That might be a question. How come iron can make 2 charges and why isn't it any other charge? Like copper is 1 plus and 2 plus, but why? So if you ask that question in grade 10, you're not going to get an answer because the answer is too complicated. But now we can answer that question. So the electron configuration tells you a lot about the ionic charges. It actually explains why certain elements have certain ions. So consider iron, which can make 2 plus and 3 plus. Now, why is that? Well, to make iron 2 plus, you have to take away 2 electrons. You have a 4s right there, and you can easily just rip 2 electrons from that. And then you have an empty s orbital that's stable, okay? You don't have a half orbital. If you have a 4s1, that is less stable, so that's what iron, iron doesn't have a 1 plus charge. You can't just take 1 from the s, okay? So if you take 2, it's more stable because that orbital completely disappears. Now, even better is when you take 3 electrons from iron, because look, you want D5. D5 is wonderful, it's stable. But right now you have D6, so if you would just take that one, if you remove it, this is wonderful. You just have 3D5, very stable. So Fe3 plus is the most common ion for iron. The 2 plus is more rare, okay? Why does iron make 3 plus? Well, because the electron configuration becomes stable after you remove 3 electrons. This is true for the other ions as well. If you consider tin on the previous page, tin has a charge of 2 plus or 4 plus. If you take away 2 electrons, you have 5s2, 4d10, and that's beautiful. Everything's full. You can also take away 4. Then you get rid of the 5s2. You just have a 4d10. A full D is stable, is wonderful. You can't have tin 1 plus. You're not just taking 1 electron from tin and you leave with a 5p1. That is so uncomfortable and unstable. That just doesn't happen. So electron configuration explains a lot of the ionic charges. Okay, so just make sure you know this little detail. So here are some practice questions. Let me just remind you, a lot of these are exceptions and some of these are ions. So I'll give you around 5 minutes to work on these. You don't have to write the full notation, just write the core because it's simpler that way. And then I'll take this up in 5, so compare your answers with mine. All right, so go ahead and try. All right, so for the practice, first one, you get silver. And if you do enough of these, you're going to realize silver is one of the special ones. So you actually have 5s1, 4d10. Okay, make sure you didn't miss that. If you wrote 5s2, 4d9, you don't get marks for silver. The next one will be oxide, oxygen with extra 2 electrons. That would just be 2s2, 2p6 with a helium. All right, so next one, sodium. Sodium loses 1 electron, so just bracket neon. I think we did that one already. Antimony has a 3+ ion. That means you've lost 3 electrons. So you have to write out the whole thing for antimony and then take away 3 electrons. And it just so happens that the 5p3 that was supposed to be there got removed because you had to take 3 electrons. So this is antimony. And antimony can make a charge of 3+ or 5+. And you can clearly see why. 3+, you just take away the 5p3, very convenient. 5+, well, just take away 2 more from the 5s. You will end up with 4d10, which is very stable. You don't have a 4+ because then you have to take just 1 electron from the 5s, and that's not stable. And next is tungsten. Tungsten is tricky because there are many ways to go wrong with tungsten. First of all, it has 4f14 in it. Many people forget the F block exists between the 6s and the 5ds. Second is that this is an exception. All right, so 6s1, 5d5 instead of 6s2, 5d4. And so many ways to go wrong. So you have to really pay attention to detail when you do electron configurations. A small mistake just makes it wrong. Okay. So I hope you got all of these correct, and if you didn't, remember your mistake.
I have a question.
I have a question.
Yes, one at a time.
Okay, for the second one, why didn't you write just neon? Because like.
For the oxide ion, why didn't I just write neon? Well, because if you gain 2 electrons, sure, you have the same configuration as neon, but you can't write neon because then you would assume that every electron in there doesn't do anything. Okay, the whole purpose of the square bracket and a noble gas is telling you that whatever electron is in here, they never participate in chemical bonding. So that's why I will abbreviate them with just a noble gas. Don't worry about them. But that's not the case for the oxide ion. Those 8 electrons, they did participate in bonding. That's why they got to 8. So they are bonding electrons. You can't put them in a noble gas, so you have to write them out. If you write bracket neon, that is incorrect. Now, how come sodium can write bracket neon? Well, because sodium lost electrons to get there. It didn't gain electrons to get there. So whatever electron sodium lost, that was the electron that participated in bonding. The rest of the electrons will never bond, all right, because it's inert. So that's why sodium or any positive ion can have just the noble gas, but a negative ion, you have to write out the electrons. Does that answer the question?
I have a question for the sodium, like the ion. So
Yes.
what if we write like helium and like the same like a version of
Yeah, no, you can't do that. You
can't do that? Okay.
Yeah, because sodium has to choose the noble gas that comes before, which is neon, not helium.
Okay.
If you write helium, you're telling me that all those electrons that you decided to write out, they will somehow participate in bonding, which doesn't happen. Sodium, after losing that electron, becomes inert.
Okay.
You have a lot of sodium ions in your body. That's not going to react with anything.
Okay. Thank you.
Okay, those are good questions because those are common mistakes. Any other questions?
For the fourth one,
The fourth one, okay?
the original one is KR5S2 4D13, right?
No, 4D13 doesn't make sense because D goes to a maximum of 10. The original will be 5P3 following the 4D10.
All right.
Yeah, you see what I'm saying?
Yep.
Okay, anything else? All right, good. I'm glad you asked those questions because those are going to be mistakes if you didn't ask. Okay, cool. So the next thing is valence electrons. When we learn Bohr-Rutherford diagrams in grade 10, you also learn about valence electrons. Those are the electrons on the outermost shell, and they participate in chemical bonding. So with the Bohr-Rutherford diagram, it's really easy to see which ones are valence. Just look at the outermost orbit. Oh, look, 3 electrons for aluminum. Done. But since Bohr-Rutherford diagrams are wrong, we don't use them anymore. Okay, here's an energy diagram. So can you tell me what the valence electrons are? It's a little more tricky than just a Bohr-Rutherford diagram. So which one do you pick? How many valence electrons? And if you look at the electron configuration, the 1s2, 2s2, 2p6, 3s2, 3p1. So which ones are valence and which ones are not? So what is the rule for deciding the valence electrons? So first of all, the definition of valence electrons, so we have to redefine it. We can't say outermost shell anymore. We have to say the outermost principal quantum level. So basically largest n. That's a mouthful. I really hate this definition, to be honest. I don't think it's very precise. Okay, and I'll explain why later. That's just a rule of thumb. I wouldn't just, mount that on the wall. It's not like carved in stone. So sometimes there are exceptions to that. But generally, it is the largest n. And to determine the valence electrons, you have to look at the following. Those electrons must participate in chemical bonding or has the potential to participate in chemical bonding. Okay, only valence electron bond. Those inner core electrons, they don't do anything. The valence electrons do not include full Ds and full Fs. That means D10s and F14. They're full, they're stable, they're not supposed to change. They are not valence electrons, okay? Exclude those. And lastly, if you have a noble gas, you have 0 valence electrons. Okay, in grade 10, we said that noble gases, they have 10 valence they have 8 valence electrons. Well, that's a white lie. We lie to you a lot prior to grade 12. So noble gases, we don't consider them to have any valence electrons. Despite the fact that we write it as if they do, they don't. Okay, because they never participate in chemical bonding. Okay, that's another lie, but like for all intents and purposes for this course, they don't participate in chemical bonding, so they don't have valence electrons. You see what I'm saying? So a common mistake is to write 8 for a noble gas. That's not true. Now, I don't like the fact that the definition of a valence electron says largest n, because that's not always true. Sometimes it's not the largest n. Largest n and something else could be the valence electrons. So what do I mean by that? We're going to do this together. Okay, I'm going to show you like my reasoning and why they have that many valence electrons, and then I'll let you practice. So first of all, you have 4 elements. Write the configuration and then figure out how many valence electrons. So sulfur is neon 3s2, 3p4. Okay, that's an easy one. No exception, very simple. How many valence electrons? Well, the neon core, those don't count. So what comes after? You follow the rule. The highest n, so 3. 3s2 and 3p4, so there's 2 electrons in s, 4 in p. You add them up, 2 plus 4, 6. So sulfur has 6 valence electrons. That is exactly identical to what you would have gotten with the Bohr diagram. Sulfur has 6. Okay, so no difference here. Rubidium, okay, rubidium is an alkali metal. So the configuration is just 5s1. So we have krypton, 5s1. 1 valence electron, because that's the only electron you have. Obviously 1. Everybody in the first column has 1 valence electron. That's also a free one. What about bromine? Here is the configuration for bromine. You have argon as your noble gas, 4s2, 3d10, 4p5. So can somebody tell me how many valence electron you think this one has?
17.
Sorry?
Like if you follow the rule, there's like 17.
Yeah, if you count all of them, yeah, you have 17, right? 2 plus 10 plus 5, that's 17. That is not 17. Okay, that's a common mistake. Oh, look, you just look at all of them, add them up. That's not how this works.
So you just
Remember the rule. You have to exclude the full Ds. 3D10 is completely full. And therefore, that is stable, and they won't participate in any bonding. So you cross them out, 2 plus 5, 7. Okay, so that's where that saying comes in. The highest N, the 4s, the 4s and the 4p, they give you the valence electrons. All right, you see how this works? Now, if the d orbital wasn't full, if you had 4s2, 3d1, then you do have to count it. Then it's 2 plus 1 is 3. Okay, but in this case, it is full, so you don't count it. So it's 2 plus 5, 7. Bromine has 7 valence electrons, which makes sense because bromine is a halogen, and all halogens, fluorine, bromine, chlorine, and iodine, they all have 7 valence electrons. So this matches what we've learned before. Okay, last one, krypton. The configuration for krypton is 4s2, 3d10, 4p6. So how many valence electrons?
0.
0, thank you. It's 0, okay? If you write 18, that means you added them up. That's wrong. You can't do that because 3d10 doesn't count. If you exclude 3d10 and go like 2 plus 6, 8, that's also wrong because that's a noble gas. Noble gas is always 0. Please remember that. Okay, so those are the rules. All right, so here's another practice. Many tricks are hidden in here. All right, there are many ways to go wrong. Try to fill this out. I'll give you a couple of minutes and then I'll take this up. So make sure you go through the list because you will see something like this on the test. I will give you an element or an ion or whatever, ask you for the core notation, and I ask you for the valence electrons. Okay, so you're just going to have to fill that out. So I'll give you some time, maybe 5 to 10 minutes. Like I'll give you 10 minutes because this is quite long, and then I'll take this up. All right, taking this up, the first one, lithium, that's a really simple one. So all you have to do is write the core configuration. That's just 2s1. The valence electron, well, it doesn't take a genius to figure out it's 1 because you only have 1 electron there. Neon, the configuration is 2s2, 2p6. Valence electron is not 8, it's 0 because that is a noble gas. Aluminum is another simple one, 3 because 3s2 and 3p1. Okay. Gallium, you have 4s2, 3d10, 4p1. The 3d10 does not count because it's full D. So you cross that out, 2 plus 1, 3. All right, and iodine, that's a halogen. The 4d10 doesn't count because it's a full D. So 5 plus 2 is 7. Again, all halogens have 7 valence electrons. So here it gets interesting. You have ions. Phosphorus with 3 minus, so the phosphide ion, first of all, that's the configuration. It looks exactly like neon. It looks exactly like argon. So how many valence electrons? Is it 0? Because argon has 0. No, this one is actually 8. You can't write 0 because it's not a noble gas. This has the same configuration as a noble gas, but doesn't mean it is a noble gas. So how did it get to 8? Because it participated in chemical bonding. It got 3 electrons somehow. So those electrons are not useless. They're not just sitting there. They did something. Okay, so they do count towards valence electrons. You have to say 8. So xenon, 5s2, 4d10, 5p6 with the krypton. So this one is a noble gas. So this one does have 0 valence electrons. Okay, the 4d10 doesn't count. The 5s2 and the 5p6, they add up to 8. But again, noble gas, 0. So tin 4 plus is just 4d10. Okay, and you're supposed to have a 5s2 and a 5p2. But since you've lost 4 electrons, those are gone, you just have a 4d10. And how many valence electron does this one have? Does anyone want to tell me that one?
Is it like 0 again, or?
0, exactly. The 4d10 doesn't count because it's a full D and you have nothing else, so 0. So in a metal that lost electrons, you can have 0 valence electrons. Okay, like sodium losing 1, you would have 0. Does that make sense? Lead is tricky. First of all, you have to write the configuration correctly. Right? You got 6s2, 4f14, don't forget the 4f's, and then 5d10, and then finally 6p2. So to calculate the valence electrons for lead, you have to cross out the 5d10. That is a full D. The 4f14 is also gone because that's a full F, and they don't count. So what you have left would be the 6s2 and the 6p2, and they add up to 4. So you would have 4 valence electrons for lead. So I hope you got these correct. If you didn't, figure out your mistake. And if you have any questions, please ask. Anything?
What was the thing that you were saying about the sodium wouldn't be 0 or something like that?
About the sodium having 0 valence electrons?
Yeah, you said something like that, didn't you?
Yeah. If you
The
lose
sodium
all
lost
your
one.
valence electrons, you have 0.
Okay.
There was another question? No? Okay, so let's move on to the last thing finally for today's class. This is very short and easy. Ground state versus excited state. So every single thing that we've done so far assumes that the electrons are all in ground state. That means none of them are excited. So there was no light to absorb, so none of them jumped to a higher level. So they're at the lowest possible state, the ground state. So there's aluminum again. Okay, that's ground state aluminum. 3s2, 3p1. Okay, we've learned that already. Now let's say somebody shines light on this aluminum. Some electrons, namely one of them in 3s, it got excited, absorbed the light, and jumped to 4s. Now that would be excited aluminum. Okay, so this is still aluminum, it's just one of the electrons are in a higher energy level than it should be. Now, there's no way for you to know where it would jump. It could jump to any orbital. It depends on the amount of energy that you give to that electron. If you give it a lot of energy, it's going to jump to a really high orbital. If you give it just a little bit, it's going to jump to the next one. So in this case, it just so happens to have jumped to the 4s. I chose that one because I didn't feel like drawing more lines, and it's really convenient to draw arrow to the 4s. So I chose 4s, it jumped to 4s, okay? There's no way for you to figure that out. Let me just let that student in. So, as a result on your test, I'm not going to ask you to predict where this electron will jump. That will be a very complicated question. You would then need to know what the energy of the light is, and then you have to use an equation, which we didn't learn, not part of this course. So don't worry about predicting what the excited state will look like, because you will never know that. Rather, you will be given the excited state, and I'm going to ask you to write the ground state for the excited state. Okay, that's much easier to do. All you have to do is drop that electron to the lowest possible state. So the excited state for this aluminum will be 3s1, 3p1, 4s1, and that just looks silly. So you just have to know that, oh, the 4s1 doesn't belong, because the 3p is not filled. How do you get to the 4s? Well, you must have had an excited electron. So that means in order to drop it back, you have to give it back to the 3s. All right? So let's actually look at some examples here. When electrons lose energy, it will always fall back to the lowest possible orbital. Okay? Don't fall back to something lower but not the lowest. It has to be the absolute lowest, the most you could fall. So if you look at the picture, if that's the excited aluminum, it has to fall back to 3s. You cannot fall back to 3p. If you fall back to 3p, that will still be excited. That wouldn't be ground. So it has to be 3s2. Okay, so that's the ground state. So if you have phosphorus, and this is the excited state, 3s2, 3p2, 5d1, what would the ground state be? Can somebody please tell me? Where could that electron fall to?
41.
4d1? I mean, if you fall to 4d1, sure, you're at a lower level, but that's not the lowest level. Is there a level lower than 4d that you can possibly drop to?
Oh, 3D.
3d. No, there's one even lower than 3d. It's right there, already written out. It's just not full. See what I'm saying?
3D.
The 3p, right? There's only 2 electrons in the 3p. I mean, there's still room for more. That is the lowest one. 3d, 4d, 4s, you can fall back to those, yes, but that's not the lowest one. So to get the ground state, it falls back to 3p2. 3p3. Now, if that seems confusing to you, like, wait, what if I don't see this on the test? Like, it's hard for me to figure out which one is the lowest. Well, a sneaky trick is just simply write out the electron configuration for phosphorus. Just basically ignore the question of excited state altogether. Just write the ground state from phosphorus from scratch. Start from the beginning, write it out. That should automatically be the ground state. We've learned that already. So instead of looking at the excited state, you don't even have to look at the question. Just write the ground state. Okay. The next one will be selenium, and if I give you this, you have a 4s2, 3d10, 4p3, 5s1. Where would that electron drop to? You guys hear it? Which one?
4P.
Yeah, the 4p. Because the 4s is full, you can't go there. 3d is full, you can't go there. So the next highest one will be the 4p, and that is not full. There's only 3 of them, so you can fit 3 more. So the 5s would drop to the 4p, and you make 4p4. Okay, you're getting the hang of this?
Yeah.
Last one, chromium. If I give you this, 3d5, 5s1, where would that s drop to?
4S.
4s.
Oh, damn, you guys are good. Yeah, it's 4s. Okay, that's a tricky question because it doesn't actually say 4s in the question. Okay, a lot of people are tempted to write 3d6 because they see a 3d5 and like, oh wait, that's not full, and let me just put an electron in there. In fact, there is actually an empty 4s orbital available. Now, you drop to the 4s, not the 3d, because 4s1, 3d5 is the most stable configuration. Why is the 4s empty? Well, one of the electrons just up and left because they got excited and just left. The other electron got promoted to the 3d. It was 3d4, and then it promotes and becomes 3d5. So as a result, you have an empty 4s orbital. You don't have to write an empty orbital. You don't write 4s0, so that's redundant. Just don't write it. But you have to know that it's available. It's right there. So you drop it into the 4s1. If that's hard to see, all you have to do is just write the configuration for chromium from scratch. Don't look at the excited state. Just do it. And we've all practiced how to write electron configuration of any element. That doesn't have a weird exception. So make sure that that's what you're doing. Just write the ground state from scratch and you'll never get it wrong. Okay, so on the test, I will give you the excited state, ask for the ground state, because it's impossible to predict the excited state because you don't know how much energy was gained. All right, so this is the last little bit about electron configuration. This was a really long class. I hope you guys understood the majority of, if not all of the lessons. So just to recap, electron configuration, you use the Aufbau principle and the Hunt rule. You start from the bottom. The lowest energy level, you fill that up before you go to the next one. And you pair them up only if you absolutely have to, okay? And valence electrons are the one that in the outermost, well, I shouldn't say outermost shell anymore, the highest quantum level. And okay, that's not very precise, but that's a good enough definition, the highest n values. Okay, and those participate in chemical bonding. The D's and the F's, if it's full, it doesn't count. All right, so this is all practice. Any questions? If you don't have any questions, I'm going to end the stream.